All right, so one of the undergraduate groups in the School of Computing came up with the idea that to encourage, make it easier for students to get to know professors, they would set up a trick or treat on Thursday. So in theory, you can go to professors' offices on Thursday and do trick or treat. So they say they're going to give me candy to give out. So if you want to come to my office and say hello, I'll give you a piece of candy on Thursday. And you can try this out with other faculty. I don't know how many people are going to play along. But. Okay, so PS 8 is out due the end of the week. Any questions about that or anything else? Okay. Speaking of PS 8, so PS 8, if you haven't looked yet, is you're implementing a class to represent the state of a board for the game of Connect 4. And so the board is, so many columns wide and so many rows high, and you have to, you have to keep track of the pieces on the board. And basically, the pieces can be somewhere in a grid. And the question comes up: how do you keep track of the state of the board? So let me draw you a picture to show what I'm talking about. So a Connect 4 board is something like this. And there are two players, different colors. Red and black, I think, are the ones I used. I'm not sure. Or red and yellow, maybe. Anyway, you might put a red piece here, and then the next one might be a yellow piece here, and then there might be a red piece here, and so on. So at any given point, you need to know, where are the pieces. And the reason you need to know is, for among other things, you have to be able to tell when someone has won. So if you end up with a position like this, where there are 4 in a row of the same color, then that color is won. Now, what sort of data structure should you use to keep track of the state of a Connect 4 game? Yes?
2D array.
Okay, you said a 2D array. And I recommend you use a 2D array for a couple of reasons. One, it's the right thing to use. And second, I've given you a method that'll tell you whether, given a 2D array, it'll tell you whether 4 in a row or not. So I've done that part of the program for you if you use a 2D array. But I haven't talked about 2D arrays, so that's what I want to do just at the beginning here. So you know that to declare an array, you do something like this. Let's make A1 be an array of 10 integers. Okay, and there it is. And you know how to index into the array. All right, if you want element 5, you do that. No. If you want element 5, you do that. Okay. If you want element 5, you do this. Okay. And you know how to change element 5. Something like that. And you can ask for the length of the array like that. And if you want to iterate through an array, you use a for loop. It's one way to iterate through the array. Okay, so when you visualize a two-dimensional array, you typically think of a picture of something like this. This is how I draw them. And then if I stick a 5 in it and a 7 in it and so on, it looks like that. So that should be familiar to you by now. Two-dimensional array. Let me go back to where I was. A two-dimensional array you can visualize like this thing right here. So instead of just having an index, you have two indexes. You have a row index, which I'll call I, and you have a column index, which I'll call J. And I and J can change independently, and to specify a particular spot in the array, you've got to say what row and what column. So if you say if you're looking at I equals 2 and J equals 3, Then we go 0, 1, 2, and then 0, 1, 2, 3. So this would be that cell in the two-dimensional array. So you can see why it's such a attractive way to represent a Connect 4 board. But let's see how to create them in Java, because that's what you'll have to know. So let's declare a two-dimensional array. Well, if this is the type of a one-dimensional array, we just add an extra set of empty square brackets, and that says two-dimensional array events. Okay? Or another way to think about it is, it's an array of one-dimensional arrays. And that's how it actually is represented in memory, as an array an array that contains one-dimensional arrays. And we'll declare this one B1. And if you want to create it, you say, okay, I want a new one that has 10 in that dimension. I'll make it smaller so it won't take up so much space, and 4 in the other dimension. Okay, so it's showing, what is it showing us there when it prints it out? Why did it print it out in this way? Instead of printing out as a two-dimensional grid like I was drawing, it shows this thing, and then this thing, and then that thing. So what's going on? What does B1 contain? Yeah?
2 arrays.
Okay, well, it contains more than 2 arrays. I don't think they're all shown up there. Yeah?
20 elements.
Well, you can think of it as there are 2 ways to think about it. You can think it contains 20 elements arranged into a grid, or you could think of it as containing 5 elements. And what is each of those 5 elements? Yeah?
Each element is a row that contains 4 values.
Right. Each element is an array that contains 4 ints. So like I said, it's an array that contains arrays. But you can work with it like this. You can say, okay, what is B1 sub 2 sub 3? And it'll tell you 0. Or you can say, okay, store 15 there. Then you ask what's there, it'll tell you 15. Now you could also say, what's B1 sub 3? Let's see. B1 sub 2. B1 sub 2 is going to be an array of length 4. Okay? So there's 2 ways you can play it. Sometimes it's convenient to think of it as an array of arrays. For Connect 4, it's convenient to just think of it as a 2-dimensional grid. And when you index into it, you provide the 2 indices that you need to manipulate it. Now, suppose we want to go through and store 7 in every element of this array, B1. Now, if you were trying to do that in a regular array, you would write a for loop, right? You'd say something like for int I equals 0, I is less than b1.length I plus plus. And then in here you do something to b1 sub I. But b1 is a 2-dimensional array, so we need to generate the other index. Okay, so we're letting I range from 0 to the length of b1, and then we're letting j range from 0 to the length of b1 sub 0. Why did I do that? Why didn't I just say b1.length here? Yeah.
Because on the inner loop, you're trying to go on like the array stored within the array. Seems like
Right.
pull out the first array element.
So b1.length would be 5. b1.length would be 5, but what it contains are a bunch of 4-element arrays. And so wouldn't want to let j range over the full length of b1 because it's too big. In fact, rather than b0, let me change something here. Let's do that. So we're essentially letting j go for the full length of element I of b1. So anyway, you just say b1 sub I sub j equals 17, let's say. And there is a prototypical nested for loop that generates valid indices into that array and sets every element to 17. So now if we look at what B1 is, it's a bunch of arrays of length 4, all containing 17. Yeah?
Is there a way to make it like say you will have like five arrays and they each have like lists of arrays? Is there a way to make those lists of arrays different lengths?
Okay, he's asking, do all the arrays inside of B1 need to be the same length? The answer is no. We can do something like this. We can say B1 sub 0 and just create a new array of length 8. And so we are storing a new array of length 8 as the first array contained by B1. So it's no longer a grid. The first row, if you will, has a length of 8, and then the rest have a length of 5. So now we look at what B1 is. You have that array of length 8, and then 4 more arrays of length 4. So that's called a ragged array. So you can, you don't need a ragged array for, the word I'm saying here, if you can't understand me, is ragged. You won't need that for Connect 4. But it is a possibility. Okay, if I do B1.length, what am I going to get? How many elements in B1? 5. If I ask for what's this? Yep, that's 8. That's the array I just stuck in there. If I ask for any other row, like 3, I get 4 back. Okay? So the takeaway for the assignment you're doing is you're going to want to create, if you're using this representation, you'll have an instance variable which represents the board, and you'll know how many rows and columns in the board, and you'll just create a two-dimensional array of that size, and then we need to index into it. You'll do it with an expression like that. Yeah?
I don't know if it's possible. Can you do two-dimensional arrays with array lists?
Three-dimensional array containing...
two-dimensionals with array lists.
Oh, you can do the same thing with array lists. But this is why I don't... For this problem, it's perfect because you know exactly how big the array has to be. It doesn't have to grow and shrink. So to create a two-dimensional array list, you have to say array list of array list of string equals new array list. Okay? And then you have to start adding things to it. So if you want to add to it, you'd have to say list.add new array list. Right, and now list is an array list that contains an empty array list. So you could build it up like that. What would it take to access element ij? Suppose you built up an array list of array lists like that to represent your board. What would it take to get a particular element out? Yep, you have to say list.get of 3.get of 2, something like that. Get me the array, give me the list at index 3, and then in it go to index 2. It's a lot easier to use array notation. So arrays are great when you know exactly how big they have to be. They don't have to grow and shrink. Array lists are great when the former is not true. Okay? And as I mentioned, there's a class I gave you called 4 in a row that has a method that'll tell you whether there's 4 in a row. So look at that. Now tell me, the first index, if you have a 2D array, is the first index the row or the column? I've been saying row. That's just it's whatever point of view you want to take, right? You can think of the first index as a row and the second as a column. It's just a matter of perspective. So there's no official definition for what the first index means. And you can have, 3-dimensional arrays or 4-dimensional arrays and so on. They just get harder to visualize. Okay. Next topic is I want to finish up talking about rational numbers. So last time we were implementing this class, and I've given you a problem in your assignment that uses this, so I just want to talk about the implementation that we came up with. So you remember that we're trying to represent exact fractions, rational numbers, and to do so we have an instance variable which is the numerator, an instance variable which is the denominator of the fraction represented by an object. Okay, now this was our first constructor. Well, let me skip down to this one. This is a constructor that creates the fraction n over d. And you remember what we did was we first made sure that d was not 0. If d is 0, that's bad. You don't have a fraction. Denominator can't be 0, so we throw in a legal argument exception. If d is negative, we decided we wanted the denominator to always be positive. If anything needs to be negative, we'll make it be the numerator. So I just flipped a sign if d happens to be negative. Then I compute the GCD, the greatest common divisor of the denominator and the numerator, and divide it out, just to keep things as small as possible, and store them in the instance variables. So that's what created a rational number. Okay? What's going on here? This is supposed to create the rational number 0. I didn't write it this way last time. Last time I stored 0 in the numerator and 1 in the denominator. Who could explain what's going on with this weird statement right here? You've never seen one like before. Yeah? Right, I'm calling one of the other constructors. So when you see in a constructor a call to what looks like a method called this, what you're actually doing is calling another constructor to do your work for you. So what constructor am I calling? There are 3 of them you see here. Well, they're all called rat, too. So. Yeah?
You're calling the rat with 2 parameters.
Right. I'm calling this one, and you can tell because I'm trying to pass 2 parameters to the constructor. This one takes 0, this one takes 1, this one takes 2. So basically, when this constructor is called, it just turns around and calls this constructor and passes it 0 and 1 and lets it do its thing. That's a common thing to see. And same thing down here with this constructor. We're trying to create the rational number n over 1, so we just call the 2-parameter constructor and let it do its thing. Now, there's some fine print to this. If you want to call a helper constructor, the call to this has to be the first statement in the constructor for technical reasons. It can't appear anywhere else. Now, after you call another constructor, you could do some more stuff down here. Let's type in that. But you can't do anything up here. You can't put another statement up there. First, it has to either call it right away or you can't call it. So anyway, I just wanted to explain that because it shows up in the problem set. Now, we didn't get around to implementing the numerical methods, so let's look at this one here. This is the add method, and it adds 2 rats. It adds, which 2 rational numbers does it add? Because there's only one being passed as a parameter. So somewhere, let me write it here, someone has called like r1.add r2. So they're trying to add the rational number 1, the rational number 2. Where do r1 and r2 show up down here? Yeah?
R1 is the implicit, and
Okay, so
R2 is just the R.
okay, that's the implicit parameter, and this is the explicit parameter. So r2 corresponds to r. So when this method is called from here, whatever the value of r2 is becomes the value of r, and whatever the value of r1 is becomes the value of this. So the rule for adding numbers, fractions, it looks like that. It says if you want to add a over b plus c over d, what you do is make that the denominator and make that the numerator. So you see what this method does is it takes the numerator from this. So it takes R1's numerator, multiplies it by R's denominator, which is to say R2's denominator, and vice versa. That's the numerator. The denominator is just the product of the denominators of the two parameters. So we compute n and d, and then we just create a new rational number by calling a constructor that has n and d as numerator and denominator. So this reveals something you may not have expected. Why are we able to, notice, these are private instance variables up here. Down here, I understand why we're able to get at the denominator of this. Why are we able to get at the denominator of R? Yes?
It's passed in as a parameter.
Well, it's passed in as a parameter, but if I were to pass a scanner in as a parameter to this method, you would not be able to access the private instance variables of the scanner. So what's special about R that we can get at its instance variables? Yeah?
It's because the instance variables that it has are in the same class.
Okay. So the instance basically, we're in the rat class. So we can look at the instance variables of any rat object, not just the implicit parameter, but of this one as well. So that's why we're able to do this. Now we could write it this way if we wanted to. We don't have to say this dot numerator. That's implicit, so we could take this off. But I prefer to use it in this case because it makes it explicit where the denominator and numerator are coming from. Because there's two rat objects here, and by saying this dot, it kind of makes it clear. It makes it more symmetrical, I guess. No, that's not what I'm trying to do. Okay, so that's what the add method looks like. Notice it does not change either R or this. It just creates a new rat that represents their sum. The remaining methods are very similar. The sub is almost identical, except we subtract instead of add. We're just using the rules of adding fractions that you learned a long time ago. Multiplying is really easy. You just cross multiply. Division is easy, except you need to make sure you're not dividing by 0. Comparing is easy. You just do a cross multiplication and see which side is bigger. And we did the 2-string before as well. So it shouldn't be any mystery about how the class works. There are just a few unusual things I wanted to point out to you here. In particular, the way you can use helper constructors and the way that you can access the instant variables inside any rat object, not just the implicit parameter. Okay? Now, what you're doing is changing the representation. So instead of using longs to represent numerator and denominator, you're going to use big integers. And you're going to add one more constructor that takes big integers as parameters. So you have 4 constructors in all. What's the rationale for using big integers instead of longs? What's that?
It can handle like big numbers.
It can handle arbitrarily large integers. There's no such thing as overflow with big integers, except you could overflow memory. You could run out of RAM, I guess, if the number got big enough. So that shouldn't be a difficult part of the assignment. You're essentially rewriting the code to use, instead of using the operators on longs, you're using the methods provided by the big integer class. But the first thing you need to do is to read the big integer documentation, see what the methods are called. So any last questions about this before I move on to a new topic? Yes?
I was just curious, in the event where you didn't specify the constructor, but it knew which one to use because of the number of parameters, what would happen if you didn't specify the constructor and there's 2 constructors that have the same amount of parameters? What would go?
Okay. So if I turn around and try to do this, it's going to tell me duplicate method, even though it should say duplicate constructor. So it's just telling you you've got to do something to disambiguate. So if I said like, if I pass in a character. No, let's not do a character. Let's pass a string in here. Now I'm good. Even though there are two constructors with one parameter, because they're different types, that's okay. And the same thing works. This is called overloading. These are overloaded constructors. You can also overload methods, and the same rules apply. There has to be a way for Java to tell which one you mean when you call it. So either different numbers or different types of parameters. Anything else? Okay. Okay, this is a little program I wrote. And it displays what are called Sierpinski triangles. So that is what you call a level 0 Sierpinski triangle. It's just a triangle. Now, I'm going to drag this a little bigger. Now, if that's a level 0 Sierpinski triangle, let me show you what a level 1 Sierpinski triangle looks like. Okay, so that's level 1. This is level 2. This is level 3. And that's level 10. So it's a fractal. And the question I have for you is, what's the rule for creating, how would you describe this? This is a level 1 Sierpinski triangle. So let me remind you, this is level 0 Sierpinski triangle. It's just a triangle colored in solid color. That's level 1. So if someone asks you, what is a level 1 Sierpinski triangle? What would you say? Yeah?
The triangle with the triangle equal to 1/4 of the area of the loop.
Okay, so that's a good way. That's a way of thinking about it. Is so he looked at it and noticed that when we went from here to here, what I did was I carved out a triangle in the middle, 1/4 of the size. Okay, that's one way to describe it. There'll be some problems, so let's do it. Let's do here. So how do you create a level 2 Sierpinski triangle? It's not as easy to describe in terms of carving things out. So if you took a solid triangle and you carved out, how would you describe what to carve out to make it into a level 2 Sierpinski triangle? There's sort of the middle part right here, but you also got to do these little ones on the sides. So let's think of another way to describe it. Yeah?
In space that you haven't carved, you add a level 1 Sierpinski triangle? Is that what it's called?
Yeah, Sierpinski triangle. Okay, so that's getting better. This is going to be an easier way to describe it. So a level 1 Sierpinski triangle is just a solid triangle. A level 0 is just a solid triangle. A level 1 is 3 level 0 Sierpinski triangles arranged in a triangle. Right? This thing right here, that is a level 0 Sierpinski triangle that's half as big as the original, right? This one and this one. It's 3 level 0 Sierpinski triangles arranged into a triangle shape. Okay? What's a level 2 Sierpinski triangle? It's this one, which is a level 1 Sierpinski triangle, this level 1 Sierpinski triangle, and this level 1 Sierpinski triangle arranged into a triangle. What's a level 3? It's 3 level 2s arranged into a triangle. So then imagine taking that and shrinking it to half the size and then making 3 of them to create a level 4 Sierpinski triangle. So there's your level 3 at the top. There's a level 3 in each corner. And it just goes on like that. We go to level 5. We go to level 6. We go to level 7, 8, 9, 10. Eventually we get down to, another level or two will get beyond the resolution of the screen, and certainly the projector. All right? So that's a definition of a Sierpinski triangle. Let's say a level 0 Sierpinski triangle is just a solid colored triangle What is a level in Sierpinski triangle? Yeah.
I would just say when you go up a level, it's all solid triangles will have a cutout applied to them.
No, I don't want to talk in terms of cutouts. Because you say have a cutout applied to them, it doesn't say how to do the cutting. So you had the first idea. I'll let you have the last word.
Level N.
Behind.
Oh, sorry.
Level N triangle would be made be 3 level N minus 1
Right.
triangles.
A level in Sierpinski triangle is 3 level n minus 1 Sierpinski triangles arranged in a triangle. So we describe this structure we describe what a level 0 is, and we explicitly, and then we describe level in terms of level n minus 1. So that's called a recursive definition. That's what we're going to talk about this week, is recursion. So a recursive definition typically consists of at least of a base case. The base case is the level 0 Sierpinski triangle in this case. You don't describe level 0 in terms of level -1. So the base case, there's just an answer for it. And then for all the higher levels, you have what's called the recursive case. You describe what it looks like for level n in terms of what it looks like for level n minus 1. That's called recursion. So we'll see how to code this up shortly, but I just wanted to introduce to you the idea of recursion before we did that. We'll show you some more examples before we get to code. But recursion is the technique of describing a complex thing in terms of simpler versions of the same thing. So a lot of people will say recursion is defining something in terms of itself. Well, that's a circular definition. That won't work. What's the key? What's the difference between a circular definition, which is describing something in terms of itself, and recursion? Yeah?
The n minus 1. It's describing itself in terms of its former self.
Well, I would say, yeah, it's describing something in terms of a simpler version of the same thing. It has to get simpler in some way. Because if I want to know what a level 5 Sierpinski triangle is, I have to figure out what a level 4 is. That requires a level 3. That requires a level 2, a level 1, 0, and that's the base case. So the definition ends. If I define a level 4 in terms of a level 4, I've got circular definition. It'd be hard to code up. Yeah?
Is this code on Canvas or something?
Is this what?
Is this code on Canvas? I just like the way it looks.
Yeah, so if you open up the lecture code for today, I've got an executable jar file that I'm running right now. But the actual code is up here. We're looking at it shortly. Yeah, this thing also lets you change like the colors. So you can change the foreground or the background. Oh, that's hard to look at. But. Okay? Any other questions about this? Like I say, we'll look at the code later on. Okay. Now, let me show you another idea. There is a function in mathematics called factorial, n factorial, denoted by the exclamation mark. What's the definition of n factorial? Yeah?
N times n minus 1.
Well, it's n times n minus 1 times n minus 2 times all the way down to 1. So, like, 4 factorial is 4 times 3 times 2 times 1. 10 factorial is 10 times 9 times 8, all the way down to 1. That's a function that gets fast pretty quickly. Gets large pretty quickly, I should say. Okay? So, let's see. Let's do 4 factorial. That's just 4 times 3 times 2 times 1, which is, what, 24. All right. Now, you could code up factorial using just a for loop, right? It's just an accumulation loop that starts the result out at 1 and just multiplies it multiplies the result by 1 and then by 2 and then by 3 and then by 4, accumulates an answer and returns it. So that's one way to do it. I want to show you how to think about this recursively. Now before I do, let me tell you, if you got your choice in Java between writing a loop to do something and writing a recursion to do the same thing, typically you prefer the loop. It's going to be more efficient. So it'd be hard to write a loop to do Sierpinski triangles. It's not hard to write a loop to do factorial, but factorial is a very common example of recursion, so I'm going to do it this way anyway. So here's the idea. Another way to look at it is n factorial is equal to n times the quantity n minus 1 times n minus 2 times so on down to 1. Okay, I just sort of regrouped there. But what is this right here? What's another way of writing that? The product of n minus 1 times n minus 2 and so on. That's n minus 1 factorial. So we've got now that n factorial equals n times n minus 1 factorial. So what kind of definition is that? That's a definition of factorial of n in terms of factorial of n minus 1. It's the definition of factorial of something in terms of factorial of something simpler. It's the same idea we saw with Sierpinski triangle. It's a recursive definition. That's the recursive case. We also need to come up with a base case. So in a sense, we have to come up with the base case is just the answer to the simplest version of the problem. And we're going to say the simplest version is 0 factorial, which is defined to be 1. That's just the convention in mathematics. Right? So that's another example of a recursive definition. Any questions about that? Now here's the thing about recursion. It takes a while to learn to think recursively. And I have seen students in lecture be completely puzzled, and then it's like a light switch goes on or a light bulb goes on, and they suddenly get it with a jolt. I've literally seen that happen. And a lot of students just go in thinking, oh, recursion I've heard is really difficult. But it's not. You just have to adapt your way of thinking to it. I can remember where I was and what I was doing when I first understood recursion, even though it's been like almost 45 years ago. I was working on an assignment in a class like this, and there were two ways to solve it. One way was basically with a loop, and it looked really grim to do it that way, but I suddenly realized that how I could apply recursion to solve it, and it made it very simple. And it was a really powerful feeling when I got it. So I hope you all get to experience that powerful feeling. Okay, let's look at one more example. And it's this one. This is called a pedigree tree or an ancestor tree. So it's one form of family tree. And so what this is supposed to show is we got this individual Ben who was born in 1956. Ben has a father and Ben has a mother. Ben's father is Sam, who was born in 1927, who has a father and a mother, and so on. So this gives to some depth the ancestors of Ben. Okay? Now, how would you describe the structure of this tree right here? If the word tree puzzles you, it's something like that is called a tree in computer science. But just tell me the structure of that diagram. What's it made up of? Okay, let me get you there.
In general, every person has a father and a mother, so every person has two.
Okay, so I mean, in this tree, though, not every person has a known father and mother. So basically, what this is, it says, I don't know who the father of Chris is. I don't know who the mother of Chris is. So, but yeah, that's a good insight. But yeah.
Guys, a lawn
insight is this tree here consists of a root node. It consists of Ben's information, basically Ben's name and date of birth, plus 2 simpler pedigree trees for Ben's father and mother. So the way to think about this is not as, oh, it's made up of a bunch of boxes and arrows and numbers and letters. It's made up of this bit of information here, plus this tree and that tree. Sometimes the trees are missing. That's what the slash is for. So that is a recursive definition. We're describing a pedigree tree in terms of simpler pedigree trees. So pedigree tree consists of someone's name, date of birth, the pedigree tree for their father, and the pedigree tree for their mother. So it consists of 4 things. So it's defined in terms of itself, but it's always defined, I should say pedigree trees are defined in terms of other pedigree trees, but the other pedigree trees are always simpler. They're not as deep as the one for Ben. Okay? So that's another recursive definition. Now we've said there's a recursive case and a base case. So there's one other kind of a pedigree tree besides the one I just mentioned. It's actually illustrated up there. What is it? So if a pedigree tree is either a name, a date, a year of birth, and then a father tree and a mother tree, what's the other kind of pedigree tree? Yeah?
Is it one where there's the name, date of birth, and then only one or the other?
Well, close. It's this, just right here. It's the sort of the null pedigree tree. So like, for example, Chris consists of a name, a date, and 2 simpler pedigree trees, but those pedigree trees themselves are just the null pedigree tree, the unknown pedigree trees, the simplest pedigree trees. Okay? So let's, so I'm going to let that, a triangle stand for an arbitrary pedigree tree. So there are going to be 2 kinds of trees now. There's the empty pedigree, which I'm going to describe as null, and a non-empty pedigree tree, which I'm going to describe with this picture. In other words, a name, a year, a father tree, and a mother tree. And I'm not going to show you the structure of the simpler trees. They're just some tree. Okay? So if we want to apply abstraction to this tree and show you what the Ben tree looks like if you abstract away the details of the subtree, we get this picture. Okay? So that's just saying that Ben consists of a name, a date, a father tree, and a mother tree, and says nothing about the structure of the simpler trees. What about Wayne's tree? What would Wayne's tree look like if you abstracted away the details of what the father and mother trees are? It's going to be the same picture, same sort of picture. It's going to say, Wayne has a name, a year of birth, a father and a mother tree. Those trees happen to be the null trees. But so again, we're defining larger trees in terms of simpler trees. That's recursion. It's a recursive definition. All right, we'll come back to that later. So I've shown you 3 different examples of recursive definitions. And for when you can define data recursively, you can describe data recursively, then you write code, recursive code that consumes those structures. So let's take a break and we'll start writing some code. All right, so here we're back in Eclipse, and I'm going to talk about the factorial example first because it's the simplest to implement. Here is the iterative version down at the bottom, an accumulation loop. In fact, we wrote this very loop when we talked about accumulation loops. So that's saying that, okay, we'll start the result out as 1. That's the accumulation variable. We'll let I go from 1 to n. Each time through the loop, we'll say result gets I times result. We're just multiplying the numbers one after the other. And in the end, you return the factorial. Now, what if n is 0? What's this thing going to return? Well, let's see what happens. It's going to set result to 1. The loop won't run because this condition will be false immediately, so it'll return 1. So it does the right thing when n is 0. Now, let's try writing it recursively. So typically, if you have one base case and one recursive case, and sometimes you can have multiple recursive cases, but none of our examples do, you're going to have an if statement to decide which case you're in. So we're going to say if we're in... all right, thankfully I know it's my sticking Windows key. How can we tell if we're in the base case? In fact, I told you, what is the base case? Yeah?
The base case is described without using any case.
Okay, so the base case is, you just give the answer straight out. You don't describe, you don't give the result for the base case in terms of simpler things. So the base case is the simplest case. What was the simplest case for factorial?
N equals 0.
Right, n is 0. So if n is the 0, we're going to do one thing. Otherwise, we're going to do something else. Now I need to put a comment on this method. I remembered, so I'll stick it up. I'll just copy this comment. Great. Now, if n is 0, what's the answer? 1. So for the base case is usually really simple like that. If n is 0, we just know the answer. It's defined to be 1. There's nothing to calculate. You just return it. Otherwise, we're going to use this definition right here. This is the recursive definition. N factorial is equal to n minus 1 factorial times n. So down here in my base case, I say, okay, I've got to return n minus 1 factorial times n. So it's something times n. Now, how can I calculate n minus 1 factorial? If only there were a method to compute factorial, I could call it. Do you see such a method anywhere? Let's look. Oh, here is one. It says returns n factorial when n is greater than or equal to 0. So that computes factorial for me, so let's call it. And we're done. That we just directly translated this recursive definition up here. It says that n factorial is n minus 1 factorial times n. And that's what I wrote here. N minus 1 factorial times n. And we know that, I can put the mouse over it and see, yeah, it returns the factorial of its parameter, so it's going to give me back n minus 1 factorial. Done. Okay, now there's students that want to argue about this. So I'd love to have these discussions. Does this seem fishy? Are we like getting away with something? Do you even believe it will work when I run it?
Yes.
There's some yeses, there's some nos. Okay, what would keep it from working? Those of you that don't think it'll work, what bothers you? I don't make fun of anybody. Just want to know what you're thinking. What could possibly go wrong? Go ahead.
If you're calling the method within the method of the method.
Okay, the method is calling itself. How can that work? Okay, I think you were going to say something.
Oh, I was just going to ask what if it's negative.
Ask about what?
I was just going to ask about what if it's negative.
Okay, but we require it to be non-negative in the look at the comment. Yeah, if it's negative, we got a problem. Yeah.
As long as you're following the basic steps of the loop, it'll go right. If you set a variable that keeps on iterating down, and so that it just.
So, okay. factorial of -2, which would require -3, -4, and so on, that would be bad. We'd never hit the base case. That's why I said at the top up there, n has to be greater than 0. Yeah?
To solve that, could we just put like else if n is greater than 0, do what we are
Yeah,
doing,
or-
and then else throw some exception.
Right, or we could do this. We could just say if it's less than or equal to 0, return 1. I don't do that because mathematically, actually, off the top of my head, I don't know how factorial is defined for negative numbers, if at all. But that would certainly solve our problem here. Yeah?
So for long, the variable type, how long does it actually take? Because I know that once a variable goes from a really large positive number, it will then flip to
Yeah. So with long, so I'm using longs because it doesn't take a very big number to overflow, make factorial too big to represent it in. Longs go from about -2 to the 63 to +2 to the 63. So if you started from 0 and counted down through negative numbers, eventually you get to the most negative number and wrap around to the most positive number. And then if you're doing this recursively, you'd eventually hit the base case. But it'd take a while. You'd run out of memory before that happened. Okay, so here's the most common objection to a recursive method is how can the method call itself? Isn't that going to be an infinite loop, if you will? Right? It calls itself, and then it calls itself, and then it calls itself. How does it stop? But what's the key? What's the key that makes it stop? The base case. Well, it stops when it hits the base case. But the key thing is, it's not like the method is not exactly making the same. So if we call factorial of 10, what's the recursive call going to be? Factorial of 9, which we'll call factorial of 8. The key to realize is that parameter keeps getting smaller and smaller, which guarantees it'll hit 0, and things will stop. Another objection is, if you have a model in your mind of how method calls work, suppose your model is, okay, for every method, there's a place in memory where the values of the parameters are held. Okay? If that were the case, recursion wouldn't work. If every call to a method required using the same spot in memory to hold the value of n, then the recursive call would interfere with the original call. Things would break. But it's not that every method has a spot in memory that holds the value of its variables. The point to realize is that for every method call, there's a place in memory to hold all the variables. So that works out as well. So let's run it and see what it does. Okay, so it computed factorial of 6, which is 720. Now if I go to factorial of 60, I'm not sure. Okay, it actually overflowed the longs and got into negative numbers. I think it's factorial of maybe 42 is the biggest I can do, if I remember. So that's good, but factorial of 43 is perhaps too big. Yeah. So that's the point where it gets too big. So factorial grows really fast. So we could use big integers for this and go as far as we want. Okay? You can set breakpoints if you want, but I think I'll leave that for the lab tomorrow. It's better when you do it yourself. And you'll be able to see, well, in fact, I guess I can't resist. I'm going to set a breakpoint, not there. I'm going to set the breakpoint right there in the base case, and then I'm going to run it. And over here, we see, okay, this is what was going on. We were at line 14 of main, and then line 28 called fact. So it kept calling itself over and over again until it finally hit the breakpoint. So when it hit the breakpoint, there was stuff allocated on the runtime stack that I showed you a while back, but there's sort of 42 pending calls to fact waiting for it to get an answer back. So I'm going to have you in the lab tomorrow. You'll get experience tracing through and trying to see what's going on. It's easy to confuse yourself with these recursive breakpoints, but and then if we just start stepping out, it returns, and builds up over here. Actually, I should have done this all along. over there you can see what's being returned and what the value of n is. So as I step out, I'm going to do this again. Let me kill that and run it again. I'm going to kill the light so you got a fighting chance of seeing what's up there. So you can see it's made all these recursive calls. It's finally hit the breakpoint. Over here now, n is 0, and it's getting ready to return. So what's going to get returned? So 1 was returned. It's now up to the point where n is 1, and so now it's going to return 2, and then it returns 6, 24, 120, 720. As we back out of the recursion, that's when the multiplication happens, right before the returns. Oh, so 42 is no good either. See how it went negative? And it goes back to positive. Yeah, it grows really fast. And then it finally completes and prints out the answer. Yeah?
So, will this, so 42 doesn't work, but does it work because it's an even number, or is that a false answer that we got?
It's a false answer. The real answer is much bigger than that. You're just seeing integer overflow in action here when these numbers get so big. Okay, so that's one example of recursion. Yeah?
So if we did want to find the original number and we didn't really care about all of the loose numbers, could we use scientific notation to actually find?
We could write this with doubles. But the problem is doubles are only good to about 15, 16, 17 digits, the mantissa. And so you would get an accurate answer for the magnitude of the number, but you wouldn't know all the digits. You know, it's worth looking at. It has nothing to do with recursion, but it's worth looking at. Let's change this so that it takes in a double and returns a double. And now we should be able to run it. So notice it started with 7538. If I run it with doubles, it's 1.405 times 10 to the 51st. So that other answer is completely bogus. This one, you know the first however many digits in the answer. You don't know the rest, but you know where the decimal point belongs. So it's a huge number. Yeah.
So if this were being used to calculate some position of something, then it would be in the ballpark, but it wouldn't be very exact.
Right. And if you were to compute, if you were to change this now to use big integers, the answer you got out would be 140500611, and then so on. There'd be a bunch more digits. It'd be 50 digits in all for the exact answer. Okay. Now let's look at Sierpinski triangles. So I have two classes. The first class is the main method that and all the GUI stuff. The other class has a method we need to change, but I'm just going to run it for now and show you what happens. So that's a level 0 Sierpinski triangle. If I ask for a level 1, nothing happens. And the reason is I've implemented the base case, but I didn't implement the recursive case. So let me show you we want to fix that, so let me show you this code here. All right, draw triangle is what matters. The rest is just GUI stuff. We get in, draw triangle takes some parameters. Graphics 2D, that's the object that we got to, that's the graphics object that we're going to draw with. And level is that parameter. That tells us what level of that we want. And then what do you suppose these are? What's double x1, double y1? What's double x2, double y2, and double x3, double y3? Those are the 3 points of the triangle. So look at what the base case does for a minute. I'm using graphics 2Ds instead of just plain graphics objects because it lets me specify doubles as coordinates instead of just integers, so I don't have to round to n's. What does the base case do? Someone asks for a level 0 Sierpinski triangle.
Just creates a triangle using those 3 points and fills it.
Yeah. So it just creates, basically there's a path2b.double class. Details don't matter. basically lets you create a triangle by specifying the points, and then there's a method that will fill the whole thing in some color. So this first chunk of code in the base case does the graphics for us. Now, do we need, you can see the else, that's for the recursive case. Do you think we're going to need to do any graphics in the recursive case? Turns out we don't. Every triangle that's drawn, to make a, no matter how complex the Sierpinski triangle is, every individual triangle that's drawn is going to be drawn by the base case. Be drawn in different places and at different sizes, but it's done by the base case. What does a recursive case have to do if it doesn't have to draw anything directly? Yeah?
Does it have to figure out where the points of the new triangle are going to be?
Yeah, it has to figure, remember, to draw a level n Sierpinski triangle, we've got to draw 3 level n minus 1 Sierpinski triangles. But we've got to decide where those should be drawn. So that's the work of the recursive case, to figure out where to draw those 3 triangles. Now, what method will the recursive case use to draw a simpler Sierpinski triangle? It needs to draw a level n minus 1 Sierpinski triangle. What method will it call? Draw triangle. Because, after all, draw triangle draws a Sierpinski triangle at the specified level. It does exactly what we need, so we might as well use it. And you got to make sure, the one thing you can run afoul of when you do recursion is you've got to make sure that your recursive call is simpler than the original call. If it's not simpler, then you get what's called infinite recursion, which is similar to an infinite loop. Thing just calls itself over and over again. What's getting simpler here? Yeah? The level. The level gets smaller. Now, we just need, all we have to do in the else clause right here is make 3 method calls. We need to call draw triangle 3 times to draw our 3 triangles. So let's see if we can figure out how to draw one. So we're going to have to pass the graphics object. That's a given. And we've got these 3 points. x1, y1 is 1 point, and so on. So what would be the coordinates of, in fact, it'd be better if we sketch it out here. So we got a point here, and I'm going to label that with x1, y1. A point here, which is x2, y2, and a point here, which is x3, y3. And I've somehow got to draw 3 simpler Sierpinski triangles. So this is our big triangle. How do I figure out where the simpler triangles go? Midpoint. So I've got to compute this midpoint and this midpoint. Oh, what did I do? This midpoint and this midpoint, and connect them. So this is the first triangle. One triangle is this one right here. The next one I have to draw is this one down here, and the last one I have to draw is this one right there. So what would be, how do we calculate that midpoint right there?
Sum of the points divided by 2.
Right, this one here is x1 plus x2 divided by 2, and the other coordinate is y1 plus y2 divided by 2. I just have to average the coordinates of that endpoint and that endpoint to get the midpoint. So I need to calculate 3 midpoints and for 3 triangles. Okay, so let's just do that math. Okay, G. So let's say the first one, we're going to start at x1, y1. So we're going to draw that triangle in the upper part. So one corner is a corner of the existing triangle. What are the other 2 going to be? Go back to my picture. So here is one corner. Now I want the coordinates of that corner. It's just x1 plus x2 divided by 2 and y1 plus y2 divided by 2, right? So let's type that in here. x1 plus x2 divided by 2, y1 plus y2 divided by 2. And what's the last pair of coordinates?
One plus x3.
Right, x1 plus x3 divided by 2 and y1 plus y3. Y1 plus y3. So I'll copy this here. Change this to a 3. Okay, so we've got our points. And then the last parameter is the level. What level of Sierpinski triangle do we want? Well, we're asked to draw one of level. And now we're drawing 3 of which? Level minus 1. And now I get to find out what I did wrong here. What's this? It's an extra paren there. Okay, so at least that's something. What's it going to draw? If you had to predict what will happen when I run this, where it's just making one recursive call and just drawing the upper triangle each time it's asked to do it, what will that look like? What will the level 1 look like? You're drawing in the air. Okay, go back to this picture here. If this is the space we're drawing the triangle in, and we want to draw a level 1 Sierpinski triangle in that space, what will be shaded in? Just the top one. So let's run it and see if our intuition is right. So let's see. That's saved. We'll run it. Okay, there's level 0 like before. Level 1, we just drew the one triangle upper part, right? What's it going to look like at level 2? Okay? So we're only, so it doesn't look interesting at all. It's just, it just gets smaller and smaller. Till we get to level 10, now isn't that interesting? So at level 10, you can't see anything, yet when we do level 10 with the full thing turned on, you see the pattern. I'm not exactly sure how that works. It would seem like it would be invisible at level 10, but the way the graphics works, it is visible. All right, let's add another one here, and I'm just going to copy and paste and hope I can get this to work. Now what? Is this thing stuck again? Do they sell, how do you unstick keys? Do they have some sort of stuff you spray with? I should stop eating lunch while I use my computer. Okay, so this time I don't want to start x1, y1. I want to start at x2, y2. And then we would average, let's say, x2 and x3, y2 and y3. Let's see. And then I want to do x2 and x1, y2 and y1. So I'm just computing different endpoints here. I think I did that right. Let's see what that looks like now. Level 0, level 1. We're getting a pair of triangles. As we go up, we just get nothing very interesting. They just get smaller, and eventually at level 10, you can I can see them on my monitor. And the full picture comes in. Oops. So we want x3, y3. So then x2, x3, I think if I do here, I'm okay. All right. So make those 3 recursive calls, and the Sierpinski triangle emerges. Okay. So the thing to appreciate is, what is the thing to appreciate about this? Does anything strike you? Yeah.
I mean, it looks really complicated, but it's like
Right. It looks very complicated when you look at a level 10 Sierpinski triangle, and yet the code is very simple. You know, you have to be able to draw the graphics, yeah, and you have to compute some midpoints. But besides that, it's very simple. Simple program to create a very complicated looking fractal. And I don't know how long this has been around. I don't know how when Sierpinski discovered this kind of triangle, but I bet you he didn't have much computer graphics to help him. So interesting discovery. So that's our second example of recursion. Yeah.
Struck out to me is that it very closely models what a human would do if they were to manually do it, to go through step by step.
Right. Perhaps that's what he did, was just wondered what would happen and just sketched a series out to see what would happen. Okay. Any other questions? Yeah.
I was just curious, when you're only have the two triangles and you're going up levels, like the first time when we had one, it just kept doing the top one. I was kind of expecting it always to just be
Do the top one of a bunch.
Yeah, so I was kind of expecting it always to just be the top and then the left one, but as you incremented up the levels, it seemed to shift from side
Right.
to side.
So yeah, it's a little, you know, it can get complicated to explain what's happening there, but in this version here, nothing could ever appear anywhere but in that top piece of the triangle, because these are the calls that would put stuff anywhere else. Right? So when you do it with one recursive call, you do not get a fractal. You just get nothing in the limit. Same thing with 2, but the 3 makes it into a fractal. And that's a fascinating thing too. I mean, there's a whole science of fractals. I'm just interested in here. Well, the thing that I care about for this class is the idea of recursion, which I'll just end by emphasizing that when you have a recursive program, it's typically because there's recursive structure to the data you're manipulating, as there is here. There's going to be a base case, which does not make a recursive call, just does the answer. And then there's going to be a recursive case that makes one or more recursive calls to a simpler version of the same number. The simpler is key. Okay. So I will stop here. Next time we'll look at that tree.